Hi, my name is Dan Adler. My background is in large system simulation, microchip design, and fintech technology, where I often saw systems that looked stable but suddenly reorganized. In this table talk, I'll introduce a framework I call Stability-Driven Assembly, or SDA, and use it to ask practical system dynamic questions like how do we model systems that do not just move towards equilibrium, but change the space of future possibilities. Most dynamical models move through a fixed state space. The variables, the flows, the interaction rules are defined in advance within the model. Many real-world systems behave differently. Persistent configurations accumulate. New interactions become possible. The effective rules change with the history. That is the distinction I want to explore. Adaptation inside a fixed model structure versus evolution that changes the structure itself. So the mechanism, as I mentioned, is called SDA, Stability-Driven Assembly, and it gives a minimal mechanism for this transition. You start with random assembly, but then you add persistence. Some configurations last longer than others. Because they last longer, they accumulate. Because they accumulate, they are more likely to shape future interactions. The basic idea is simple. Persistent turns random search into selection. No genes, no replication, and no predefined fitness functions are required. The reason this matters is that differential persistence is not exotic. Some things disappear immediately. Others last and stabilize and become part of the environment. That is true in physical systems, but also in organizations, in markets, in technologies, and in policy systems. In the talk, I will briefly show simulation evidence compared with unconstrained random assembly, how SDA reduces entropy and concentrates population probability mass around persistent motifs. This important point is not for this specific toy model. It has been proven in chemical systems and in other models as well. It is a mechanism. It's persistent weighted feedback that can generate selection-like dynamics. And what it tells you is that there is a direct implication to dynamic systems. Equilibrium may be real, but it may also be provisional. A system can remain in a quasi-stable regime until a more persistent configuration appears and reorganizes the flow. That gives us a way to think about punctuated change, stability, disruption, and a new regime. I'll translate this into examples that system dynamics people care about. In markets, persistent strategies can create niches for new strategies. In organizations, persistent operations, metrics, and workflows, and other tools that emerge can reshape what the organization is able to do next. In policy systems, programs, agencies, and constituencies can become part of the future policy landscape. These are evolving state spaces, not just evolving dynamical systems. So what is the practical payoff for people who are working in the systems dynamics area? I'm going to propose two ways to use SDA, especially together with your existing stock and flow models. One model might be to build an SDA-like entity simulation alongside your model. The other uses your model's equilibrium state as a starting point and then stress tests it with candidate disruptors to see what could reorganize in the system. So the goal is not to replace system dynamics, it is to add tools and modeling where equilibrium is vulnerable to evolutionary change. If this connects to your work, I'd love to discuss it. What are the persistent structures in your model? What makes them stable? And what could punctuate your equilibrium?